Start recording. Hello everyone, good morning or good evening based on your time zone. Welcome to this weekly discussion of lit code practice. Last week we discussed about disjoint sets, and this week we couldn't see any problem last week. So we'll try to go through a few problems that we can solve using disjoint set. Some of this problem can only be solved efficiently using union find or disjoint set. Just quick show of hand is everyone aware about what is disjoint set and how to write code for it? You can put your comment in the chat. Okay. All right. Okay, I see many no's. Then yes, we have a video recording of last Sunday session where we talked about implementation of disjoint set in detail. Since there are many no's, I'll quickly go through it. We will not go into theory why it works and how it works, but I'll show you the quick way how we are trying to write disjoint set code, and then probably similar code we can write in our interview also. So let me share my screen. All right, okay, yeah. Can everyone see my OneNote?
Yeah.
Okay. All right. So quick discussion about disjoint set. Okay. So the way we are maintaining disjoint data structure is maintaining the parent pointer in array, right? So let's say that we have eight elements in array, and index is basically it says element, and in the beginning basically they are the node parents. That means in this we have eight sets. Now when we say that connect 1 and 2 or union 1 and 2, basically based on what logic we apply, one of these become child of another. Now in this case, 2's parent is 1 and 1's parent is 1, right? Now when we say that connect 3 and 4, similar happen, and basically this is how we change the parents. So 4's parent is 3. Now when we connect 1 and 3, we can either connect, let me do one more thing. When we connect 3 and 5, when we do weighted disjoint sets, basically we make smaller node to the child of bigger node. So in this case, 5 become child of 3. Right? When we connect 1 and 6, basically 6 goes child of 3. Now when we connect 3 and 7, 3 and 7, basically 7 goes as a child of 3. Right? And now when we connect 1 and 3, basically both are both heights is same, but 3 is bigger than 1, so 1 becomes child of 3. So in that case, the 1 will be child of 3, right? So this is weighted union find. Now suppose we want to connect 8 and 2. So obviously 2's parent is 3, right? Because we go from 2 to 1 to 3, and 8's parent is 8. So size of 2's parent, that is 3, is bigger than 8. So 8 is going to be child of 3. So, but when we do path compression, right, what we do is that all the node that we visit, when we try to find the child, when we try to find parent, we also mark that node as a child of parent. So in this case, we visit from 2 to 1 to 3. Now 1 is already child of 3, so we make 2 also child of 3. So this is path compression. So weighted is when we basically compare the size of the number of element in the under the parent node, and then make a bigger node. Yes, make the smaller node child of bigger node. And path compression is when we try to find the parents. Basically, we try to reduce the depth of the tree. So in this case, if we suppose for any reason, if we have this kind of structure, right, and when we say child, when we say who is parent of 9 in that query, basically we change 9 and 6 both parent of 3. So our tree kind of become flat. Okay, any question about this explanation?
So basically, we are just concerned about the parent and not the parent. I mean the root, not the that 1 was connected to 2 or 2 was connected to 1 before. So we kind of lose that data, right?
Yes, of course. Yes, very good point. Basically, we lose the data how they are connected. Once they are child of 3, we just know that all are child of 3. We don't know whether the one was child of 3 through 2 or something else. And that is why, I mean, it's basically become the whole set. They belong to set. And this data structure doesn't give you saying that how you are a member of that set.
Yeah.
Does that make sense?
Yeah.
Okay. All right. I'll show you quickly this code because if the problem is related to disjoint sets, most of the time the actual code is nothing. So you might end up implementing a disjoint set. Okay. Let me share the screen. Okay. Can you see my OneNote?
Yes.
Okay. So we are going to quickly write disjoint set. code. Okay, so we can name it anything. Whenever we write a union find, we are going to write a union find with the path compression. Weighted union find with the path compression. Okay. Is font size is okay to see on Zoom?
Yes.
Yes.
So we basically maintain parents and our root, whatever you name it, array of root. We maintain a similar array for what is that size, and we maintain the count. That basically say how many connected components I have in my this data structure, right? And it takes the size. That basically means that how big my disjoint set is, and we basically initialize root is equal to.
Sorry, are you typing? I couldn't see anything.
Okay, you are not seeing my screen, right? Or are you seeing my screen? Is that everyone seeing my screen?
Yeah, I can see it.
Yeah, we can see.
Yeah, you're able to see it.
Okay, let me fix it.
Okay.
Maybe in rejoin.
Cancel and rejoin.
Okay. Yeah.
Okay. So we basically said that how many elements I have in my disjoint sets, and that big two array initialize root and size, and the count is initially n. So okay. Also, we mark as we discussed, right? We mark everyone its own parent. So I run a for loop. And I say that root I equal to I, and their initial size is 1 because they, they are their own parents and they don't have any child right now. So I equal to 1. Okay. Can you please help me with what are other functions we have in this set?
Find.
Yeah. Fine. And what is the return type?
Return type is int.
Right. Yeah. So integer p. And what we do here?
We actually go in a while loop, and then we compare p with its parent. If it is not equal,
yeah,
then
so,
we go in that. Yeah.
Right. So whenever the p and root of p are equal, right? That's that we can't go anymore, right? So we go from child to its parent to parents, and when the parents and its index are equal, the value that is stored at the index and the index is equal. That means that is the root node of that connected component, and we can go, for right. So yes, we can do while loop if we do iterative. And last time we learned that the depth of this tree won't be bigger than 5, right? For all the practical purpose. So we can do recursive call as well. So if the first thing is that if root, what is my condition? If root of p is not equal p, right? then what I do is that I say that root of P equal to find of root of P. And I return root of P. Does it make sense? We have written a little bit bigger code last week. Let me see if I can find that. Click find, weighted click minion. And this is with the path compression, right? So this is the code that we wrote last year. Since it is iterative, we basically find the root, and then we try to set that root for all the path that we go through, right? But you can as well. Oh, okay. Never mind. You can as well write this way, where it's a very simple code and it's a recursive, and when we call in recursive, whatever the value that returns here, basically we keep setting on its path. So it's okay. It's very simple. Does anyone have any question about this?
So this takes care of the path compression also.
Yes. So when I say
Okay.
that root P equal to, so if I just simply return this is not, there's no path compression here. But if I do this, that is path compression.
Okay. Thank you.
So with path compression, that size array does not make any sense, right? If we
No.
go with path compression.
So that's correct. So we are going, so size is not required for path compression, but let's see where it is required. Okay, because we are going to do union find, weighted union find with path compression.
Okay.
So when we will use size to track its weight. Okay.
Okay.
So Bhavesh, should we not update the size as well when we are shifting the subtrees towards the root side?
Okay. So here is my question. When we make one, when we do the, so you are saying that in the find, right?
Right. Yep.
We are not changing who's parents and who's child, right? So, for example, that way, let me show you. I think we have an example also here. Okay, so in this case, right? Is that the example? Okay, we are saying that find 10, right? So basically, after that query, 8 and 10 both will be child of 0, right?
Correct.
Does that mean 0's number of child is changed?
No, but child of 8 has changed, isn't it?
That's correct. But yes, very good point. But when we write our code, we just, when we compare, we are never gonna work the child element, in future.
Sure. Yeah, got it. So basically,
Yeah,
we are always, I mean, the algorithm is dependent on the root nodes. So size of root node, so we can leave the leaf node aside for size part. Right?
Exactly. So that's a very good observation. So if you look at the child data, their size and other stuff, especially their size, it will be different. It won't be correct, but we never touch that.
Got it. Thank you.
Okay. All right. Okay. So what is the other function?
Yeah, but I have a question. Why the size of the root is still 1? It seems like the size of each node is 1, right? Even the root too.
In the beginning.
But at the end, it's still equal 1.
No, because we haven't tried the full code.
Okay.
We have just tried the find. Find is one of the method. maybe let's
Yeah.
say that internal
Yes.
or private. Yeah.
Yeah, union and is connected.
Okay. Yes. So integer is connected. No, is connected is Boolean, right?
Yeah.
Right. And union is probably void, right?
Yes.
Now both will take 2 points. Two element. I think this code is very simple. What did we is connected? How we see that if two elements are connected or not?
We just find the root.
Five
Check the roots.
Yeah. Return
Find
Find
of P
P
equal
equal
to
find
find
Q.
of Q.
P equal to find of Q, right? Okay. Now let's talk about union. So we said that we are going to do weighted quick union with path compression. So when we say that, always remember the path compression happen in the find method. Basically, path compression happen when we go through the whole path. That means when we try to find its parent. So we go through the whole, depth of the tree, and that time we take care of path compression here. When we say that weighted union find, so basically when we connect union, when we connect two component, we decide who is going to be child of who, and that time we decide that by looking at the size, right? So in this example, anyone remember what we do first?
So
Yeah,
we
the
check if they
parent
already
do find.
connected.
Okay, that's correct. We check if they are already connected, right? So I am gonna say that root P equal to find P, right? Integer root Q equal to find Q, correct?
Mm-hmm.
And if root P equal to root Q, then we simply return. We don't have to do anything. If they are not equal, that means both belongs to different parents, right? Then
we should check the size of these roots, and whichever is bigger becomes the parent.
yes, so make smaller root. What happened to my spelling?
But we are actually compressing the path, so why we are actually checking the size?
That's correct. So when we do the find, actually not checking the size. The moment we do the find, we are compress the path, right?
Yep.
Because compression of the path happen here. Is that correct?
Yes.
Okay.
Yeah,
Make smaller root.
but only the compression will happen only if they are present. They are already connected.
Wait.
The compression happens anyways, no?
See,
Yep.
the find is to find their parents, right? If they are their own parent, there is no compression. If they are the immediate child, there is no compression. I mean, there's no effect of this code. But if they are at the depth, right, as we discussed, see, in this case, if I say find 6, there is no change of 6 parent, right? If I say find 0, there is no change, correct? But if I say that find 8 or find 10, there will be change for the parent of 8 and 10. if I say find 10, there will be change of 10 and 8. Both parents will change. If I say find 8, then only 8's parent will change. 10's parent won't change. So 8 will become child of 0. Are we clear with this?
Yeah.
Okay. So every time we call find, unless it is the root or its immediate child, in this case, if you see this image, if they are like 9, 6, 3, 1, and 2, there is no change in parents happen. Code execute, but there is no effect of it. But the moment we go to the second layer and below, or their parent will change. And again, just repeating again, find operation won't change the overall size of the root node. It will definitely change the size of, let's say in this case, if I say find 10, 8 size will change, but it doesn't matter. Parent size will still remain same.
So when Bhavesh, you say size, it is basically we are tracking the depth of the tree from that node.
No. So okay, there are two ways to do it. Okay, when we say size, there are two ways to do it. One is so there is a, when we say that weighted Indian find, right? So either you can track the depth, and that is called rank. I mean, in Indian find lingo we call it rank, but yes, it's a depth. Or another is you basically just blindly go with a number of elements in that in that tree.
Okay.
Okay. All right. Okay. So now we want smaller root child of larger root, right? Or let's say that we make smaller root. Yeah. Point to larger one. Yeah. Okay, so in this case, basically, what I'm going to check is I'm going to check size of what?
Root P.
Yes. Size of root Q, correct?
Yep.
So in this case, who becomes child of whom?
P is child of Q.
Yes. P is child of Q. Correct?
Yeah.
And whose size will change?
Q.
Oh, sorry.
Correct. Okay. Else it is other way around, where we can say that parent of, oh wait, nobody noticed that, right? We are calling it root, right? Okay.
Yeah.
And root of Q equal to root of P, right? And size okay. So here we basically utilize size array as well as we update that when we make one root child of another root, right? So one parent child of another parent, they are merging, so their size is changed, and we simply add its whole size. And also we utilize size array to figure out which is bigger.
So your size is height of tree or number of nodes in the tree?
In this case, size is number of nodes in that rooted tree.
But okay.
I guess you have some doubt. I'll quickly show. We discussed this in last session. Basically, when a small tree and large tree, right?
Yeah.
So this is what do. Large, in this case, it's a large by size. And we make its child, the smaller always make child of larger tree. So that we always maintain at most log n depth based on if you see the binary tree, right? How
Yeah.
many, what is the depth of my tree for the n number of node? We did discuss about this, and we maintain that. In fact, we maintain much more smaller because with the path compression, but we at most maintain log n depth. Okay. Now,
Yeah.
you know, if we do the, having said that, if we maintain the height also, there's no problem. That also work beautifully, same way. Okay. The reason I choose to maintain its size is because, you know, it's the same question that we discussed, right? If I'm doing path compression, my height is keep changing.
Yeah.
Remember? Now,
That's great.
if I want to do weighted with the path compression, and if my weight is height, then my code becomes much more complex. Every time I do find, I have to figure out what is the height of this tree, and I have to go through all child. So if I'm simply doing path compression, I can do height and weight both. If I want to do path compression with weighted, you know, with weight, then it makes sense to have you know, number of node as weight or to measure size. Okay.
Could we visualize the path compression on line 17?
Line 17.
Yeah.
This one?
Can we draw some note and see how it
Yeah, of course.
goes?
I'll quickly. Let's see. Okay. All right. So okay. So we have a two component. 1 and 4 is you know, root for all the components in this union find. Now let's say that we are calling union of 7 and 3. Okay. Now this union, first thing we call is a parent of, or the first thing we say is find of 7, right? Find of 7, and then we call it find of 3, right? So when we call find of 7, what's the code we have written there? Find of 7. What we have written is that if root of 7 is not equal to 7, right? Then
Right.
basically I should draw this also, right? Then it will be very easy to understand. 1, 2, 3, 4, 5, 6, 7, 8. I have 8. No problem. Okay. So once parent is parent 1, 2's parent is 1, 3's parent is 1, 4 parent is 4, 5's parent is 4, 6 parent is 4, 7 parent is 5, and 8 parent is 8. Okay. Now root 7 is not equal to 7. So what I'm going to do is that from here I'm saying that root of 7, right? So this is our root error. So root of 7 equal to
Find of
find of root of 7.
Yeah.
What is root of 7?
5.
Is 5. So this basically kind of calling 5, right?
Yeah.
So from there, this goes find 5. Right? What does find 5 does? Again, same thing, right? If root of 5 is not equal to 5, then it is calling root of 5 is equal to find root of 5. Root of 5 is what?
4.
4. It called 4. Now it called find 4. So from here it goes find 4. Now find 4, we say that root of 4 equal to 4, right? This condition will meet, right? Correct?
Yes.
So we are going to return from here. So this return, if you see, we are saying that return whatever root of 4, right? At the end. So this is returning root of 4. Root of 4 is 4 basically. Now, when this call returns, right? What is going to set at root of 5? Value?
4.
4, right? So previously it was 4. So as I told, nothing. So if for the root and its immediate node, there won't be any height. There won't be any change, right? So in this case, although we execute this statement, there won't be any change. Okay. Now from find 5, we return what? Root of 5. Is that correct?
Yeah.
At the end. And that root of 5 will come here and root of 7. What is that value?
5.
4.
Sorry, 4. Yeah.
4, right?
Mhm.
So we set root of 7 equal to
4.
Okay.
4. Is this clear now?
Yes.
Okay. All right.
Thank you.
All right. So, okay. Okay. So as we see, right, this code is very simple and you should be able to write that pretty quickly. We took a little bit more time because we were going through it, but if you have to just write the code and you know this code, right? We have to basically write the constructor and 3 function. Out of this, this is the function where you have to make sure that you don't make any more mistake. Otherwise, this 2 is simple. There's a one more function that return count of, there is one thing we forgot here, if anyone remember.
You need to decrement the count in the union.
Exactly. Right? And when we do that?
At the end.
At the end. So if we are, merging to root element or to parent element, we basically decrement the count. Okay?
Yep.
And this count will return number of connected components we have. All right. So enough about this. I thought I will make it short, but that's fine because this understanding is very much required. Okay. Now let's go through a few problems. One is a redundant connection. I'll go through this 4 problem. We'll see how much time we have. Okay. Redundant connection. So redundant connection is a problem 684 on lead code. And the problem statement is, in this problem, a tree is an undirected graph that is connected and has no cycle. Now, this sentence doesn't make sense. If it is an undirected graph, there will always be cycle, right? Okay. sorry, that is fine. It says that tree is an undirected graph that is connected and has no cycle. That statement is correct. Okay. Sorry about that. That's correct. Now, what they have given is that they have given, you know, in a graph that is started at a tree with n nodes, and there are n distinct value 1, 2, n, with one additional edge, and this extra edge basically makes this tree looks like graph, right? In this case, let's say that 3 edges are given: 1, 2, 1, 3, and 2, 3. So 1 and 2 and 1 and 3 are there, and then there is a 2 and 3 also. So if we want to say that this is a tree, you know, we can't say right now, right? Because there is cycle, right? So what we have to do is that we have to return the edge that can be removed so that the resulting graph is a tree of n nodes. And if there are multiple answers, basically we have to return the last occurrence of edge. So for if we have to make this 1, 2, and 3, whatever this tree is whatever tree is given, right? If we have to make it a tree, which edge we can remove?
2, 3.
2, 3. Can we remove 1, 2?
Yeah.
And we can remove 1, 3 as well, right?
Yeah.
But they have told that it was told that we have to remove the last one. So in this case, if all are candidate, then 2, 3 is the one that we should return. Because the last occurrence of the edge that makes it non-tree. That is preventing it to be tree. Now in this case, 1, 2 is this connection, then 2, 3 is this connection, 3, 4 is this connection, and 1, 4. That's the one that is making it cycle, correct?
Yeah.
Now we can remove everything, anything, 1, 2, 2, 3, 3, 4, but as because of the condition that is asked to us, we will remove 1, 4 and return 1, 4. Okay. Is everybody clear about the problem?
Yeah.
Yeah.
Okay. Any idea how we can solve this?
I can take a stab at that.
Okay.
So this is pretty much the application of what you just explained in the union find.
Yeah.
Maybe we can, so we have the number of nodes, I guess, or maybe we can just find the number of nodes which are there based on the edges and create our union find data structure with that many nodes. So in the first example, we have 3 nodes.
Mm-hmm.
So we can have 3 elements in our union find. And for each node, we will, for each edge in the input, we can run the is connected and the union methods.
Okay.
The moment we see that is connected is coming as true for a particular method, that means that those 2 components were already connected, but that edge is trying to connect them again. That would be the edge which is a redundant edge.
Perfect.
Yeah.
Okay. Just one thing. Let me copy something from here. Okay. So we don't basically we already written the this class, right? So we are going to have a union find class, right? So what I'm going to do is that I'm just going to copy it here. Okay. I don't want to waste time. In interview, I might have to write it from the beginning, and this is exactly the same class what we have just written. See, count, connected, find, and union. Is this? Oh, I made a mistake. Right? Is that correct?
Yeah. But you are doing the same thing in the else part.
Yeah, of course. I'm going to change that. I mean, I made a mistake both places. Right? Okay. All right. So this is exactly the same union find code what we have just written. Okay. Now, anybody want to try it out here or whatever you explain? Okay. Going one. Anybody want to try writing this code? Don't feel afraid because union find class is already there, right? And it is working. I copied from the accepted solution. So don't worry about that. Okay.
So how do we write? Would you give me the access or should I write it somewhere
Yeah,
else?
I can give you the access because union find is here if you want.
Okay, I can
Yeah.
give a try.
Okay. So remote control, give access. Can you ask for access or you cannot?
I'm not sure. I am not.
Okay, what is your
Bhumik. Okay, I'm asking for the access request.
yeah, okay. Yeah. Okay. There you go.
Okay, awesome. So yeah, my first requirement is that I need to find the n. So maybe I'll just get done with some null checks or things like that. But the main part is
Okay, I'll give you some hint here. Okay. So yes, whatever you're doing, probably that also. Okay, this condition definitely we need. Okay, edges are null then.
I maybe just return null or can.
Okay.
I don't know. It doesn't really matter.
Yeah, that's fine.
Yeah.
But I would suggest that if I did not read it, but these are the things that we ask interviewer, right?
Yep.
And it is never null, but that's fine. It doesn't hurt. Okay, state doesn't hurt.
Makes sense.
Now, so another thing is that suppose there are 3 vertex, right?
Yeah, actually, I got the hint. Maybe let
Yeah,
me
okay.
try that. So here they are saying that there will be only one redundant edge.
That's correct.
That means that if I have n edges, that means I have n nodes in my list, because 2 edges can help me with 3 vertices.
Yes.
So 1,
So
2, and 3 can give me 1, 2, and 3. And if I have 2, 3, that means that is an additional edge. So here, if there are n edges, I have n vertices.
perfect. So that's very good. So what we're trying to do here is that, see, if I have an n vertex, then if I want to connect all vertex with one another without having redundant connection, that means I need to have a n minus 1 edges, right? Everybody clear about that? And in this case, they already told that they have given one extra edge that we have to find out, so that we can simply assume that the length of the given edges array are the number of vertices.
Yeah.
Yes, go ahead, go on.
Okay. So just taking that in a variable for simplicity. And then I'm instantiating my union find data structure. Okay, so I instantiated that with that many nodes, and now I'm gonna iterate all the edges one by one, and then I'm gonna run union find on each of the edge by taking the vertices one by one. So now I'll just let me just check how does our connected or union method look like. So union Okay, union will just do the union and okay. So if union find dot, just give me a minute. I'm just trying to remember the names.
Disconnected.
Yeah. Of 0, 1. So if they are connected, that means that this is the edge, which is a duplicate one. If that is not the case, then I would just connect them. The union method. Okay. And I think this should take care of returning if there is always a redundant edge. And just so that this compiles, I'll put a return.
Okay. So since it is C#, just let me do few adjustment. Okay, the code is perfect. I'm just making.
Oh, okay. Actually,
That's fine.
I prefer C#. I work in Microsoft, so
Okay. All right.
I didn't realize that. I usually interview in Java.
Okay, not a problem. I think this is the only change I made. Okay, I did for each and then the length. Okay. Yeah.
Okay. Shall we try?
Yeah.
You need to remove the bracket from the int, I think, in the for each.
No, that would be the edge. Edge is an int array
So
itself.
edges is a two-dimensional
Oh,
array,
it's an
right?
int array. Okay.
So
okay.
we are
I see.
giving
Okay.
0 and 1, right? So 0.
So in
Yeah,
the
one
else
more.
part, isn't the edges, so each edge is already connected, right? So can you explain what the else part is this doing union find and unionity again? Aren't they already connected?
So for each edge, what we are checking is edge is giving us a connection, that is 1, 2 means that they are supposed to be connected, right? So in our data structure, which consider that as a graph, in that what we are saying is 1 and 2 really connected in our graph which we are creating, our union find structure. When it comes for the first time, it won't be connected because we are getting that information for the first time that, hey, there is a connection between 1 and 2. So our data structure will say, no, they are not connected. Hence, we will connect them.
I see. Okay.
Then we will do it for 1 and 3. That will also be a new information because 1 and 3 is like coming for the first time.
Sure.
But when we say 2 and 3, we have a way to go from 1 to 3. So we don't really need 2 and 3 because 1 and 2 is connected, 1 and 3 is connected. So 2 and 3 at that time for our union find structure will be a redundant because it will already be connected.
So the output depends on the order in which input is given. Does that matter?
That is correct.
Yeah, I think so.
And that is why to get the perfect output, they put this condition saying that if there are multiple, just give the last one.
I see. Okay.
Yeah.
So there could be many nodes, but as soon as we find the circle, then we return it. We don't need to traverse all the edges.
That's correct. And do you know the reason?
Yeah, because if it's already a circle and it guarantee there's only one extra edge, right?
Correct.
So
Yeah.
we can remove and then we return it.
Yes.
On line 4, there is, I think, one error, which is like a union find. Its spelling is correct? I don't know.
Yes, 14 number is wrong. There is a typo there. On line number 14.
Yeah, that's fine. We'll try to run this and check. Okay. Oh, yes. You know why? I have a typo there.
It's connected.
It is just connected.
Yeah.
Okay. And that also spelling is correct. Okay. That's fine. Now.
The reason is the union class is from index 0, but the question is from
Yes. Perfect. Yes, that's the problem. Everybody understood the error?
Yeah.
Okay. So what would be the solution to this?
Edges.length plus 1.
Is this fine with everyone?
For the line 14, I prefer to decrease the edge 0 by 1. Edge 0 minus 1 and edge 1 minus 1 to transfer from the index from 1 to index from
so 0. See, both is fine. If I put line 8 plus 1 is fine, or if I decrement every time I check, both is fine, by the way. Do you all agree?
Yep.
See, if I say that I have a 4 element, then it starts with 0, but I'm not going to use 0. I'm just going to use 1, 2, 3, and that's fine, right? Then my code is simple. I have just put an extra and I'm ignoring 0.
Though I'm not sure about the implementation, but that may be an issue if we increase the length, because that will increase the internal count.
So length doesn't increase the internal count. If you see that many, it's just increase the size of root.
Oh, you see that line number 31, the count,
yeah.
and that returns the count. So number of connected component.
That's correct. I mean, a very right observation. But in this case, we are not utilizing count. I completely agree with you.
Right. Yeah. Here in this case, that will not be an issue, but
yes.
Yeah.
Yes. Very good observation. Okay. Let's see. All right. Perfect. So if you see this actual code, if you already have union find, it is very less, right? So you probably end up writing this also in your coding interview if somebody asks. Okay.
Bhavesh, can you quickly this
yeah. Yes, go ahead.
I just want to see if you can walk through this once.
Okay. Yes. Sure. Okay. So see, what we are doing here is basically we are given the edges, right? And this edge says that 1 and 2 are connected. Basically, edge in the graph says that 2 vertices are connected. 1 and 3 are connected. 2 and 3 are connected, right? And we have to. Then there is one extra edge is given so that this whole structure can be tree, but instead, because of this one extra connection, this can not be tree. It can be graph only, and we have to find that and return that. Okay. Now, what? So here we are utilizing union find to keep track of which are all component is connected. So when I say that 1 and 2, right? We come here. In first 4 is there will be 1 and 2. We say that whether they are connected or not. In our current union find, there's nothing is connected, right? In the beginning. So I come in the else part and we mark 1 and 2 as connected.
Yeah, I want to see that code.
Huh? You?
I want the code for union.
Union? Okay.
Because when you are doing it, I'm also doing on my end, but I'm getting errors. So that's why I just want to see what I'm doing wrong.
Okay, see this. I can paste this code in chat if you want.
Yeah, just paste in chat and then you can move forward.
Okay. All right. Okay.
Can you paste the entire union find class? Yeah.
Yes, I'm just going pasting entire union find class. Okay. I did not copy. Looks like. I'm just copying the union find. Okay. Oh, okay.
And Bhavesh, if you don't mind, can you again tell me why the issue around index starting from 1?
Yes, sure. Okay, I'm pasting in 2 parts. Maybe there is a size limit. Okay, till return P, and then this is the remainder of the part. Okay, so we are saying that why we did +1, right?
Yes.
Okay, so when we discuss union find, right, our whatever array we make here, right, it is 0 based.
Yeah.
Right, and the
Yeah.
input is 1 based.
Why do you say input is 1 based?
Because there's no 0 to 1. It always starts with 1 to 2, and that is what it
Oh, okay. Okay.
given
Got
also.
it.
If you see,
Yeah.
that is 1 to n.
Okay. Yeah. Okay.
Okay. So just to compensate that, we are saying +1. So 0 we just ignore. Otherwise, when we did not do that, basically when we try to get 3, we are getting index out of bound because this array just up to 0, 1, 2 index.
So if the starting value was not 1, but let's say these were random integers,
yeah,
would that change the data structure, or would it change the usage of the data structure?
Okay, that's a good question, and probably in one of this whatever the other problem we are going to see, we might find that issue. So there are 2 options to do that, right? One is that first you, based on the input, you figure out how many elements you have. So you go one pass and figure out how many elements you have. Okay.
Okay, then you instantiate
and then second.
Okay.
Otherwise, I think everybody must be familiar resizable array, right?
Yeah.
And
yeah, okay.
I did not make this union find code complex, but instead of integer, I can have a resizable array.
Okay, got it.
And if I have given, any time whether there's any index P or Q, or when in the find or in the union, anything that goes out of my array size, I basically resize my array. And then what are the new things I point, those will be with this value. So whatever the extra element I add, those all element will start with, their own root and the, okay?
Okay.
Yeah. Okay. There is other technique also. We'll see that, okay, in a moment. So everyone okay with this code?
Yes.
Yeah. So Bhavesh, one thing I want to ask.
Yeah, go ahead.
Yeah. So basically, I see in lot of union find solutions of other people, they don't take this size array.
Yes.
And they directly do operation on the parent array.
That's correct.
So, I want to, and they claim that time complexity in that path compression solution is constant for both union find and find set operation.
If they don't take the size,
yeah,
and this is, it is constant.
Even if they take size or not, if they use path compression now, then the time complexity is constant. That some function, inverse Decrement function, something like that.
I'm sure that just path compression won't give you that. Hold on. Let me open the OneNote. I mean, we did discuss that last time. Okay. So quick find, quick union, and then did we put somewhere complexity? Yes, weighted quick union. So you are saying that just path compression.
Yeah.
And you get everything as 1 constant.
Yeah. So not exactly constant. So what they claim is time complexity for operation is O of some alpha n. Alpha n is the inverse Ackermann function, which is very slow growing. So
Yeah.
for
So yes, I think that is what we also discuss here. It is alpha n. So if you see that this is that complexity. So for 2 raised to 65k, it's height of the tree is 5. But maybe it is true. Okay, I don't know. I followed this algorithm through this book, Robert Sedgwick algorithms, and in that, this is what discuss. And I believe that, but in any case, the tree weight. So tree depth can be okay. Tree can grow. I think that is very weird, right? If I don't take the weight in account, then my tree can grow in one side, right? If I have 1,000 element, they can. Oh, I think that is completely wrong. Yes, I'll tell you why. Okay. Just quickly.
Yes.
Okay. All right. Let me see if I can share my screen again. Okay, good that you point, but I think it is wrong. Can you see my screen? Or not yet?
Yeah, I think I am able to see it. This trees are
No,
drawn.
no,
No. Okay. Yes. So okay, I think I made some mistake there. Okay. All right. Okay. So let's say that we are not using size, right?
Okay.
So my tree can grow like this. Correct?
Yeah.
Okay.
Yeah.
Now my tree is like that, right?
Yeah.
Now I am saying that find 2, 1.
Okay.
Or I mean, whether 2 and 1 are connected or not. Then I can compress only 2, right?
Yes.
2 is already compressed. I'm not going to do anything.
Yeah.
Now I say that find 3 and 2 is connected.
Okay.
Right?
Yeah.
So I'm gonna do. I'm carrying basically 3 and 1 is connected or not.
Okay.
So in this case, I'm going to compress 3.
Okay.
Right?
Yeah.
But the whole other path will remain same.
Yeah.
Right? So I think the whatever amortized time and analysis we get with this result, it might not be what is that? It might not be the Akamai function, whatever we discussed.
Yeah. So Bhavesh, one thing I would like to highlight here. So for example, you have added around 7 edges over here, right? 8 edges. So if you do say find of 1,8, then entire tree will get compressed.
That's correct. So, but we are saying that, yes, go ahead.
No.
Sorry.
So it will be amortized in sense for say once in 10 operations, you will have to spend 10 units of time, and one time, and for following so many times, you will have to spend only of 1 unit time. For example, when we use resizable array, so the amortized time of insertion at the back of the array is O of 1. But even if it does that resizing and all those things, so once in a while it will resize, and after that lot of time it will take constant time. So I think something similar happens here as well.
Possible. Okay.
Yeah, yeah. Can I?
Yeah. Just go ahead.
Yes. Can I try drawing?
Yeah. You want to try drawing here, or you want to do it on your screen? Both is fine for me.
Either way.
Yeah. So ask for control, and I shall.
Okay. How do I request the control?
Let me see if I can. Oh, I can't say
Otherwise,
that.
I can share my screen, I think.
From the
Okay.
view options, drop down from the view options, you can request control.
Yeah, I'm not seeing the request control.
Okay, you can share your screen.
Okay.
Yeah. I'm just gonna stop my.
Oh, sorry, I have to keep leaving the meeting every time I do this. Just 1 second, sorry.
Sure. Yeah. So whatever we just discussed, it might be true. Okay, I might have to go and look, because in that book there was told that with both of this, the complexity is that inverse combine that function log of.
Okay. Yeah. So because Bhavesh, I don't know the rationale behind that, but that constant time thing is true because I have used in a couple of programming competitions and I have gotten accepted. And after a post analysis, I found that it's 1. So I was actually looking for the proof of that.
Yeah, possible.
Yeah.
I mean, the book that I referred to says that proving that it is a constant time is out of this book.
Yeah, actually every text says the same thing.
Yeah. Okay.
Is my screen visible?
Yes, we can see.
Okay.
3. Yes.
So, right. So the case like we're thinking of is where we have path compression, but we're not tracking size, right?
That's correct.
Yeah.
So I'm just thinking, like, let's say you have like two things like this, like one on the left is like fully compressed to 1, and then like the other side is like a linear side. So I'm just thinking, like, if you're not tracking size, like let's say you do a union on 1 and 6, right?
Yeah.
And let's say it just so happens that you do it this way, where like 1 starts to point to 6 and 6 becomes the root. So then like you've lost all of this compression that like was here previously. And then you have to like rely on calling union of like 2 and 6 to compress it back to 6.
Okay.
But wouldn't you have done a find on 6 as well? Or no, hold on. 6 is itself a root, so find of 6 wouldn't compress it. Yeah.
Right.
No, that is fine. So what is the problem here?
So I'm saying, yeah, the problem is like, let's say if you were to do a union of 1 and 6, I'm saying that like previously all of 1's children were compressed, right? Like they had a path length of just.
Yeah.
So if you don't track the size, then it's possible that when you do the union on 1 and 6, that you do it this way, where 1 becomes a child of 6 and 6 becomes the root. So then all of 1's children then like lose the compression that you had, like it becomes longer than 1 path length.
Yeah, but this longer is only for 9, 8, and 7. If any query that comes for 6, 5, 4, 3, 2, it is fine, right? And the moment.
Well, because like if you do let's say if you do like find 5 and 6,
it's fine.
Then it will compress to 6, but initially it'll still be pointing to 1.
No, it won't compress to 6, right? Oh, I see. Okay.
Like after you do the union from 1 to 6.
I agree. Yes.
So I'm not sure. I guess like it's still.
Yes, that makes sense. Very good point. Yeah.
But in this one,
I mean, if you keep on
right?
querying, keep on querying, let's say it's long, there are many query operations. In the end, it's going to stabilize to 1 node with all the children, right?
No. But we are doing extra operation. In this case, 6 could have been child of 1, and so that we never had to compress 2, 3, 4, 5. Now, since 1 becomes child of 6, whenever the find query comes on 2, 3, 4, 5, we are again compressing it to 6.
Yes.
I see. So you're trying
I
to
think that's the
save
point. Yes.
Yeah,
a
so
bigger
that's the point.
size.
No. So
the point is
already, basically, we are saying that we already, if we say that we find the amortized cost, right? We already given that cost. Now we are incurring that again.
yes, like this section was like already the most optimal configuration.
Optimally compressed, yeah.
And,
yeah.
And then,
cost is given already. The cost of compression is already spent. Now we have to spend that cost again.
yes.
Yes. I think Anik, that is yes, that is to the point, I believe.
So here what we are saying is that, hey, the size of 1 was more than the size of 6, hence merge. But what if the size of 6 was more, like there was a very straight line in under 6? What if that was longer? And
Yeah. That's correct. But see, to prove that things are wrong, we have to just find one case that is wrong, right? I agree. So in that case, what you're saying, because when I was explaining, I did that, right? I had a one long error. But let's say that let's take this example, right, to prove our assumption wrong. So on the left side, the cost is already spent to amortize, right?
Yep.
6 I can make long, and 1 I can make even bigger. 6 can have a million node in a single line, but 1 can have a 1,000,001 node. And all are directly children, because everything cost is given and everything is compressed, right? And now imagine if 1 becomes the child of 6, and then all the 1 million node, we have to compress it again whenever we make query.
Makes sense.
Yeah.
Yes.
You lose the compression that was done on
But
this.
that is only if 1 is bigger than 6 in terms of size.
Yeah.
Yes. I mean, you can't see that. That's why it says that the proof is outside, is because the proof of these things is very much depend on the way the calls happen of union and connect, and how the data, how the incoming data is.
Yeah.
Okay.
Makes sense. Yeah.
Okay.
Yeah. If you see in that book, the author says that it's out of this book, but then he ran some simulation and he put the output in the textbook print, saying that without this compression and everything, how your tree looks like, and with compression, how your tree looks like.
Okay.
Compression and the size tracking.
Yeah. Both. Yes. Yeah. Very much important. Both.
Yeah.
Okay.
So, if asked to justify the complexity in the interview, then how should you defend that?
I mean, I believe nobody will ask, or you can also say that I refer this book and that book says that out of this thing. I mean, I would not go in that much detail, right? Because I try to understand. I think I try to search also, and then it is all mathematical. I mean, it is beyond I found it is beyond my capability. So that is what I'm gonna do if somebody asks.
Okay.
For this.
Yeah.
Okay. All right. Good discussion. Thank you. Thanks, Hanif, for that point. That was very important point. Okay.
Yeah.
All right. So I think we are good with the first question here.
Yes, I think.
Okay. Good. Let's move to the second question, right? That is sentence similarity. This is the one that Hanif, we were trying to do yesterday, and then we decided we'll do today, right? Is this the one? No.
No, actually,
that was different.
I think that was different.
Yeah. I have that also. Not a problem. I think it is this one.
Yes.
Right. Okay. We'll do that also. So let's start with this. Okay. So again, as always, I'm gonna give union find here. Okay.
Okay.
So that class is here. Let's discuss and see how we can solve this problem. So this is sentence similarity problem. On different forum, I have found this question. This is, I think, paid question probably. Looks like.
I think it's remember.
Okay. So if you haven't seen this, maybe I'll give some time to read it.
Yeah, sure.
Okay. Maybe everybody can read it for a minute or so to understand what it is. Okay, so we are given two strings as an array of words, right? Words 1 and words 2. And those are basically string: great acting skill and fine drama talent. They have already broken with the words. And we are given a pair of similar words. That means great is equal to good, fine is again good, acting is drama, and skill is talent. Okay. And what it says that the similarity relation is transitive. So that means great is equal to good and fine equal to good. That means great and fine also equal. A equal to B and A equal to C. That means B equal to C. Right? This is what this says. Transitive. So what we need to find out in this is that by given pair of similar words, we have to compare both string and say that if both strings carry the same meaning or not. Okay, and pairs will be 2. There are the length of each word, I and pairs. Okay, so maximum length of the word is 20. Is there any question about Christian?
So I think the assumption here is that we should just take the pairs as the first element of word 1 is and first element of word 2. That becomes our comparison as well. We cannot say that great and drama should be the same meaning. It should be great and fine, acting and drama.
Wait, so these are the input string, words 1 and words 2. So we have to compare and say that whether great is equal to fine or not, acting equal to drama or not, skills equal to talent or not.
Got it. Okay. Okay.
Okay. And for that comparison, we have to use this, pairs what they have given with the similar meaning.
Yeah.
Okay. All right. Is question clear to everyone?
Is the size of word 1 and size of word 2 are the same?
It cannot be. And if it is not same, that means we are going to say that it is not similar, right?
Okay.
Yeah, somewhere it was mentioned that it has to be the same. If they are not same, of words in both the sentences, then it's not similar.
It is mentioned that? Okay, yes.
Yeah, somewhere here. I forgot where exactly I wrote that, but it was somewhere here.
See this one. This last paragraph, finally. Right? Can everyone see?
Yeah.
Okay, yes. So in that case, we have to return false. All right.
Okay.
So let's go ahead with the approach, okay? There can be many approaches for this problem, by the way.
Okay.
Anyone willing to give a try? Share their thought.
What I'm thinking here that the first actually build a dictionary based on the pairs to count that how many number of distinct word we have to put in our structure.
Okay.
And that will give me the size to initialize my union find data structure. And after getting that, then I will put all these connection in that union find data structure.
So, yeah. And
then we can actually get
when you say there's a distinct number of words, so that could mean there could be duplicate somehow.
Oh yeah, if you see in the example, great, good, fine, good.
What was the question? Sorry.
Oh, the question was like that there could be duplicate. I want to see the duplicate, but yeah, I understand now.
Okay, all right. Sure. So what first condition is, I'm assuming that nobody want to write the code, right? So I started writing. Somebody want to write the code? I'm just writing first condition, so you still have a chance.
Okay.
I didn't get that. Is yes or no?
Yeah, I can write. Actually, I can try.
Okay, just go ahead.
Yeah. So, shall I open this on my browser and share it?
Yes, please.
Okay.
You already have a union find class?
Yeah, I'll have to create it. So
Okay.
I did it another way in which I didn't use the size. So if that's okay, so I can use that one.
Yeah, that's fine. And we'll just time this question till 10:45 so that, last 15 minutes we can discuss this question also, okay? It's just for the interest of time, because we did not discuss this question yesterday also, so I don't want to skip today as well.
Okay, fine.
Okay.
So just let me open it.
Okay. Stopping my share.
One approach right now of size, otherwise you have to understand something different.
Say that again?
I'm asking, like, that's a suggestion. We should stick to right now one approach. If you are trying different approaches, get confused.
Oh, you are saying that. So I think approach is same. It's just that the implementation of union find is different. So internal detail about union find is different.
So you can abstract it out actually in your thoughts. Are you able to see my screen?
Yeah.
Yeah. Okay, fine. So it's my DSU class.
So DSU is disjoint,
Yeah, disjoint set.
And internal implementation is different, but it still have a find, that is find set here, and union.
Yeah, so I have created a hash map here.
That's fine. So let's not go detail about DSU, I think.
Yeah, okay,
because that's where the confusion will come, right?
Yeah,
is that okay, Asim?
Yes, that's fine.
Yeah, so implementation can be whatever we discuss or this, right? It doesn't matter, because it gives you the find, it gives you union, two methods. That is most important.
Yeah.
Okay.
So
or is connected. Do you have is connected here?
Is connected?
Yes.
No, I don't have that.
Okay, then I think we will stick to that approach where we use union find, okay? Because I'm not sure this is there is one way to solve it, but I'm not sure if this is the.
No, so basically for is connected, what I did was I was finding set of both one and checking whether they are equal or not, parent. So I was
Okay. Yeah. Please go ahead.
Yeah.
Then. Yes.
Yeah. So I don't have that in function.
Okay.
Yeah. So then what we can do, we can just iterate the pairs. List of string. It's one pair, and we have pairs. So then we will also create our DSU class. Then we'll do DSU dot union of pair dot get 0 and pair dot get 1. Then so we have found all of them. Then after that, what we can do, we can iterate for both the words. We have already taken into the account that length will be equal. So I will not be focusing on that condition here. Yeah, so I think here we will have word 1, which belongs to array words 1. Am I audible, right?
Yes.
Yeah. Here we have words 2 from words to I. Then what we will do, string p1. It's for parent of 1. So DSU dot find word 1 and p2 of word 2. Now we will check if P1 dot equals P2. So if they are not equal, then we will return false. Yeah. Here we will return true. I think one more thing we will have to handle for the words which don't have any similars. For them, our DSU will return null. So we will have to take that into account. So how we will do that? So we will only compare this if P1 is not equal to null and then P2 is not equal to null.
Okay.
Yes, I think this should work.
And move that condition in the beginning for short circuit.
Yeah, that one first.
Null condition. Yeah.
And at line 4, you might want to pass that list in the constructor.
In line 4, no. So basically, I am iterating it over here now. So I am no, actually, yeah, you are right. I will have to pass it into the constructor. Yeah. Pairs. Yeah, I think it should be fine now.
Okay.
So
I
parent will not equal to null. Cannot find symbol.
I have one question here. So doesn't the DSU needs the length of the array to be initialized?
So yes, that's true. So I think now I get the Asim's point. We had a different implementation. This is different implementation where it internally is map, okay, of the disjoint set. So this also works. I have seen this problem, but I hate when I have to change my data structure. Let's say union find what I used to write, right?
Okay.
So this is fine. You can make it run. Then I'll show you the other one also where we don't have to change it. Okay.
Okay. You mean underlying array?
Yeah.
You're missing new, I think. You're missing new keyword for DSU, I think.
Okay.
New. Find is find set.
Oh yes. Find set, and union is union.
Yeah.
Wrong answer. So I think we will have to alter this condition if both of
Should this be or P1 not equal to null or P2 not equal to null?
Yeah, I think this should be or, because one of them can be null.
Yeah.
Yeah.
So P1 equal to null or P2 equal to null, then
P1 equal to
no, that's a problem. P1 equal to null or P2 equal to null. P1 equal to null or P2 equal to null, and then there is a not outside.
So you do one more or there.
Yeah, I think this is also wrong.
So basically, if P1 is null, you return false. If P2 is null, you return false. And if both of them are not null, then you check for equality. And if the equality is also false, then you return false. So it should be all ors.
All ors, yes.
Yeah.
Okay.
And then you can remove the not.
No, if I remove not, then it will
keep
be
the not. Keep the not. Keep the
not will be there.
Oh yeah. Okay. Yes.
I'll just refer my code once. How I did it. So parent word not equal to null, and parent word dot equals parent word 2. Okay. I think did it long time back. Parent word 1. So if both of them are equal, not equal, then definitely we will return false. And if parent word 1 is null,
So another condition is both words are equal. You don't have to go to dictionary because you might not have that word.
yeah, right. So
Word 1 equal to word 2, you don't have to even look.
yeah. So
Sense, but actually that condition is not invoked in the given input. So I'm not sure whether adding that condition will.
Okay.
Yeah.
Please don't pronounce. Okay. Yes.
I'll copy it for now. I think this should work.
Parent word is not there, right? So
P1, P2.
Yeah, just I'm fixing that. 1 and word 2, and it's P1 and it's P2.
And here also not equal to null. Yeah.
P1.
Yeah, that's fine.
Where I am messing. If word 1 equals word 2 and P1 it's not striking actually why it's
Should
not.
it be so? If word 1 is not the same as doesn't equal word 2, that means they are not related. So shouldn't there be a or condition instead of and?
Here you mean?
Yeah.
No, but it is not condition. So if both are not equal,
Then you want to return false right away, right?
Yeah.
No. That if both are not equal, then we want to check if they are equals through
Right.
our transitive.
Yeah. So basically, if both of the words are not equal, then only we are checking. If they are equal, then anyway we are good to go. Yeah. Then what we are checking if P1 is not.
We can see the submission that you have probably.
So
time. Yeah.
So
there's nothing changed below, I believe. So whatever change happened, it happened above. So I think the things that we are missing is probably this one.
Yeah, this part, no?
Yeah.
Actually, we have to explicitly apply compression on all of them.
Yeah. So okay.
Make sure they align.
All right. Yes. It's not a compression. I think if you go in your solution.
You also don't have P1, P2 in the other one, right? Like
I have parent
here,
word 1, parent word 2, no?
but then you don't have the word.
No. See, you are missing that for loop that you already have. You have to pass the pairs, but then you have to do this also. You are not doing a union.
Okay.
That is the thing that is missing.
Okay. I think.
Okay.
Yeah.
So there was no union till now. Now you got the union. Because
Right.
constructor doesn't do that. The constructor does something else. Now.
Okay. In constructor, I was only making. Yeah. Right.
Okay. Now, I think this is gonna work probably. Yes. Okay. So thanks, Arpit, for sharing this. I still would like to go through the other way because so to me, right, I have understood the code one way and then I have to rewrite the code completely because I'm given the word now and I don't know the length. It is a little bit difficult for me because then there is a more chance that I'm gonna make mistake, right, in my coding.
Yeah, right. Of course, I would like to learn another one as well.
Okay, all right.
Arpit, quick question. So in your code, if you go back to the code, first you build the union, and then why did you have to do the find? Because to do the compression.
Yeah. So basically, all the words in one component points to the same parent to ensure that thing.
So you can either do path compression while doing find or
okay, that's what is yeah.
So
okay.
Okay. All right. So let's quickly. Okay, here. Right. So since we don't have time and I want to still cover the second problem, I'm cheating here, okay? And I'm gonna take the code that I submitted.
Okay.
And basically copy it.
You can actually click edit from here, so it will automatically copy it there. Okay.
Yeah, but I think I had made a same mistake in the Indian file code that also, because I copied from one single source. Okay.
Okay.
So this condition is fine, right?
Yeah.
There's no change, right? Now, what I'm doing to see, till now, this is my class, right? I'm very comfortable writing this class. I know it's integer base 0 to n, and I have less chance of making mistake here. So I want to utilize this class, right?
Yeah.
Now, but I have given a strings. Right? Now, one way is that I modify my strings to say that root is strings and do all the stuff, right? But then I lose this thing.
Yeah,
right? Root I is equal to I can't do that, because now if I make the root as a string, what I do here?
We can use
I mean,
generics.
I can make the same string, and yes, but you know, it will become more and more changes you have to make, and then maybe you might end up making error, right? So for this kind of input, what I would like to do is that I would basically convert all input and assign them unique integer. Okay, and the easy way to do is this. I have a dictionary of string and integer, and I go through all pairs once, you know, and assign them unique integer. So if the word is there in the dictionary, then nothing. But if word is not there in the dictionary, I will put that in the dictionary, and then I am assign them unique integer, and then I am incrementing that also in. So the first word will get 0, second word will get 1, third word will get 2, the new word. And that way I have a dictionary that basically tells me, you know, each word and then its unique index.
Okay.
Okay. And then it is nothing, you know, simple. Now, this is the only new code that I'm going to return. Otherwise, everything else is basically my old code where, you know, I do the union find. This is a word index, okay? WI, that's a dictionary. How much ever count, that many, you know, words I have. And basically I go through each pairs and I make union of it, okay? Right?
Right.
And, and then basically it's simple. If words and word 2 is equal, I'll just continue. If the word is not there in the dictionary, any word is not there in the dictionary, or if they are not connected, I return false. The both words should be there in the dictionary. If any word of a given word is not in the dictionary, or if they are not connected, they are not same, I just need to find the one wrong. I return false, otherwise I return true. Okay.
Why you hadn't need to do that explicit path compression which I was doing?
Sorry?
I was doing explicit path compression. You remember?
Yes.
Yeah. Why we don't need to do that here?
The union already do it, right?
We discussed till now, right? Union find this class, what I'm used to write, it already does path compression.
Okay.
Find operation takes care of the
find operation. Yes, find operation take care of path operation. This union operation take care of weight.
Okay.
So you know, all solutions are correct. I'm not saying that the solution is wrong. The problem is that if I have to change my whole class and implementation just to, you know, because my input is different, then it is very difficult. That happened in the graph also.
Yeah, right.
So the easiest way is this, you know, you assign them 0 base index and then go with the algorithm that you have learned without mistake.
Well, we can add another constructor in our generic union find to accept other data structures, and then you don't have to add any code in the.
I completely agree. It can be T, you know, it can be generic UF of T, right?
But integer is faster than the string, so you know we go with the integer.
No. I'm not saying to change. No. I'm saying like another constructor For example, I don't know how to say it. What can you go up a little bit?
Yeah.
Yeah. So this from line 5 to line 18 or 17. So that we can put it in our generic class when we're in our union find class, where we can actually instead of string we can specify another data type in. We can still do it with the integers. We're not gonna do it with strings.
Yes, but
Kind
then
of like a utility method.
I need that here also. While passing the connected, I need that index also information outside.
Yeah, but we can get that from the class itself.
Oh yeah, okay, understood. So you are saying that pair that index inside itself, yes?
Yeah, yeah. So the next time, for example, if a string or any other object, we can just pass it in and do the rest.
I think I completely agree with that. I would rather put it outside. The reason, okay, so there is I didn't want to go in that side discussion, but just Google for symbol table, okay?
Google for what?
Symbol table.
Mm-hmm.
Okay. That's the data structure that basically we don't normally use it, but search with that author name. And you get implementation of that, okay? And that is basically okay. This symbol table is a generic class that does all that stuff, okay? What we're talking, and it is generic, so you can use it with the graph. You can use it with anywhere where you need that functionality, okay?
Okay.
So I want to keep it outside, but yes, we can do other way also, okay? All right.
Cool.
Just for the interest of time, I'll quickly go through the similar string group question.
Oh, could you also copy the code to the Slack? That only
yes,
that piece.
I'll put all this code what we have seen here on Slack. Okay.
Okay.
Okay. All right. So similar string groups, right? So this is the question that we wanted to discuss yesterday and we couldn't. So basically, we are given a strings, and strings are similar if they are basically all strings are anagram, right?
Yeah.
And strings are is similar. We consider them similar if only change happen with 2 characters.
Okay.
Right. So here these are similar because swapping at position 0 and 2 basically that's become arts.
Okay.
Right. So those we call it as a similar string. And what we have to find out is that given a list of strings, basically, we want to find how many similar groups are there of similar strings. So in this case, tars, rats, and arts are similar.
Okay.
So in this case, we need to build our union.
Yes.
Okay.
But to find out they are similar or not, we basically probably have to write some code, right?
Yeah.
So, sorry, I mean, can't you just, do we really have to use union find? As we come across each string, we just sort it up and put it in a hash map.
No, that you will not be able to tackle that case. Now that 2 characters can be different.
Only 2 characters are different.
Yeah. So if
sorting, if you sort, then you lose the position information.
Yeah, that is already mentioned that all these words will be anagram.
Yes.
Yeah, that is
Anagrams
already
are
mentioned.
not just 2 position, right? I think.
So we have to actually find if there is only more, the difference is more than 2, then those are not the same. Same word.
So they have qualified the definition of anagram.
Okay.
I mean, anagram is not just by 2.
No, they're anagrams, but they're not necessarily similar according to the definition of similarity in the question. The definition of similarity is if only 2 positions
only
can
2
be
difference,
swapped.
2 edit distance. Okay.
Yeah, just a swap, like swap 2 characters in one string to another string.
Okay.
So that is correct. I mean, anagram is something different, but here we are giving meaning to similarity.
Okay.
Okay.
Right?
Okay.
Okay. Any question about this question?
No, I'm thinking.
Question is clear, right?
Yeah, right.
Okay. All right. So again, for the interest of time, I would like to, basically go through the solution directly. It internally uses the same union find, okay? And it is very simple code. So just give me a second, okay? I'm trying to project from the different screen. Can you see my other screen?
Yep.
Yeah.
Okay. Okay. So okay. So see again, if you see below, we have same union find class. There's no difference. Okay. I have the mistake that I have done before, but it doesn't matter. Okay. Here, let me correct. It's the same class, right? Now I want to utilize that class, right?
Mm-hmm.
So now we know the union find. It is very simple. Basically, whether to decide whether they are strings similar or not, right?
Mm-hmm.
The easiest way to find out is that if they differ by 2 position. Because in the question already it is given that it is anagram, so we are going to find all character in both string, right? If only 2 characters are different, that means I can replace that 2 character at most, and I can call it similar.
Okay.
Yeah. So is this fine? Is from line number 17 to 30? Does anyone have any question?
Pretty
No, I think that's
straightforward.
fine.
Say that again.
I think that's fine.
Okay. Yeah. Okay. That's what I hear. Okay. All right. So now what I'm going to do is that, if they are similar, I'm going to do union find. But then basically what we are going to do is that going through the whole string and compare with all other string. So I take TARS and then compare with the rats, arts, and star, right?
Okay.
Then take the rats, then compare with the arts and star, and then take the arts and compare with the arts and stars. If they are similar, I will basically do union.
Okay.
And finally, I just return the union of count, basically the count that we are tracking.
Okay.
Okay. And this is the answer. Basically, this will give us how many groups of strings are there. Those are similar.
Okay.
Okay. Any question?
So complexity here will be n square log n, right?
That's correct. Let's
Okay.
discuss about complexity. For other problem also we haven't discussed, but yes.
I have a question, Les.
Yes.
String, we have the string right here. We don't need to, in this case, we don't need to map the string to an integer.
Yes.
It's not
and
like
you
the
tell me,
previous one.
that's very good observation. Can you tell me why?
Because we only look for the similarity. I think
that is not the thing.
Yeah, looking at
We are using the indexes
This is the
actually of
index.
those. Yeah.
Yeah. See, previously we used that specialized structure because we are given a strings and there is no index attached to it. Now we have in this example we are given array of string, right? And array again start with the 0 based, and each string has a unique index is attached to it.
Okay. 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 Good
So,
utilization of this. Yeah.
So if you see line number 9, when we say that union, we are not passing string. We are actually passing the index of string.
Okay.
And when we want to check is similar, actually we are passing the actual string and say that whether the string are similar. If the strings are similar, basically we are merging the index. Okay, does that answer?
Yes.
Question?
Yeah. Is this the best solution for this?
I don't know what is the best solution. Oh, okay. So
I mean, in terms of time complexity.
I think so. Yes,
Okay.
go ahead.
I tried with the BFS for this. Then I tried with this ranking thing, and then I tried with this path compression. And with path compression, I get the best runtime.
Okay.
So
also this thing. This is basically we are trying different states here. But then I tried all these union find things, and with path compression, I got the best runtime.
Okay.
Hey, thanks, Asim, for sharing. So nice of you. Tried everything. So, of course, this can be solved using BFS also, right? DFS. I mean, using a graph algorithm. But it will be costly because you have to go through similar things again and again. And we know that disjoint set or union find gave us time complexity of O of 1. Constant time complexity of connecting two, and basically find if they both are connected or not.
So I found the other thing. I'm not sure because they didn't give too lot of examples. So I thought there is some transitive relationships also in this question.
Yeah.
There is because they're anagrams. So like if they're similar, if like you could only swap like two positions, right? So I think that plus if they're anagrams makes it a transitive.
So
similarity is like transitive.
A and B are similar. B and C are similar, then A and C are also similar. That's why
Yes. Otherwise, the union find wouldn't work. Like I think transitivity is like the key property for union find.
Yes.
Yeah. Agree.
But if A and B are similar in different, on different index, and B and C are similar on different index, and how could it be transitive?
Because they're anagrams. So like.
But at most you can swap only one index, right?
Right, but so since it's only like one swap, like let's say like it could be a different swap, like but still only one from like A to C.
I think if you can read the paragraph together, this form two connected groups, and there's explanation, right? Formally, each group is such that a word in that group, if and only if it is similar to at least one other word in the group. So one thing is that we have defined the similarity, that is in this paragraph, where, for example, they are differed by at most two, right, position, and we have to find a group of things. Those are basically those are not all are have a difference of 2, but these are connected by the difference of 2, right?
Oh yes, sorry, yes, that's correct.
Yes. So transitivity is not, I mean, I think that is the main thing. That is what we have to find it out here.
And that's how this count minus works out. So basically, if something we have already seen together, that's why might be if you go down. Yes. So we are doing this count minus. Yes.
Right. Line 75.
So we are sending two different words, but we seen a transitive relation earlier. So that's mean. So at line 64, we just return. That time we are not doing a count minus. So basically, they already belong to same group. We are only doing a count minus if we are finding a new
group.
We are putting them in that tree for the first time.
Yeah. So this is actually easily think as a graph problem, where tars is connected to rats, right, by the condition we have given that at most they differ by 2. Right? Is that both connected? TARS? Yes, TARS connected to rats. And rats connected to arts by 2.
Yes,
Although if you
yes.
say that TARS and arts are not differ by 2.
So technically what we can do is if I start with TARS, if like if I do breakfast search, first I'll find all similar things to TARS in an N scale kind of thing.
Right, right.
After that, I will make them, whatever I've seen them, I'll also make them visited. Then again, I will do rats. Again, I'll go through all of them. And again, I will pick arts. And then I have to also to maintain this transitive relation. Like if TARS was connected to other guy, and that way I have to do this thing. Or might be you are already sharing a solution.
Yeah. So, so if you are doing no, I'm not sharing that solution, Asim. So this can be solved without union find. Basically, we build a graph.
Yes.
Okay. So say that TARS and rats are similar, then connect them. There's a path between TARS and rats, and then there's a path between rats and arts, and star doesn't have any path. And then to find out if basically then you apply the algorithm of finding the connected components in graph.
Yes.
Okay.
I think if I'm not mistaken, I think almost every like union find problem can be solved with the graph, but it'll just be like much more extra work possibly.
Exactly. Yes. Yes. So union find will drastically reduce the time complexity. Okay.
Also, it's much more quicker to implement union find.
Yes, I agree. I mean, once I had some hesitance. I mean, I always hesitate, but once I learned this union find, simple way, this code now I can write anytime.
Yeah, right.
It's
just 5 minutes.
Yeah. So if you, I mean, this is kind of basically Dijkstra algorithm or BFS, right? You basically practice so much, you can always write it, correct? And then it's just a matter of using it.
Yeah, agree.
So how to make the intuition that this if any problem can be solved by union find?
So basically, the key thing to observe is the transitivity.
Yes.
Someone made that point, but that's actually a good point. So I couldn't recall the case when you will be able to use union find without transitivity. Because without
if you consider the previous problem, like the similar string groups. So if we didn't have transitivity, then we would not be able to use the
But find. if you have to find islands, there is no transitivity connectivity there, right? So still you can find with the union find.
So
I think that there is also transitivity connectivity. So for example, 2 elements at the start of first row are connected. Then third element on the same row will be connected with the first element as well.
So transitivity, that doesn't means that A equal to B, B equal to C. That means A equal to C. But that also means that, I mean, as per my understanding, okay. From A you can go to B, and from B you can go to C. That means from A you can go to C.
Yeah. So that is the thing to observe in the island problem, right?
Yeah.
Okay, fine.
I think one of the intuitions I look for union find, I just got to learn it today, but the intuitive thing I see is that if you need to find some groups, then you can consider union find and then try to see what defines the transitivity in that problem. And if you can do it, that means that maybe you will be able to solve it using union find.
Yeah. When I learn it, what I used to do is that I would always see this kind of problem as a graph problem, right? And I can solve all of this, what we discussed right now, using graph, all of this.
Okay, yeah.
But then graph has a worse complexity because I'm not utilizing a lot of things of graph, but basically I'm kind of utilizing, if suppose I convert this problem into graphs, right? I'm utilizing saying that whether A and B are connected or not.
Yeah.
You know,
So,
through
yeah.
some path. It doesn't matter direct or indirect. Now, similar things I can find using union find also. Exactly similar thing. So union find give me that same answer in O of 1. But graph always I have to iterate.
Can it be applied in dependency?
No. Right? Because you have order in dependency.
Okay,
so that's the graph, but that's a directed graph.
Got it.
Right? So you can go from A to B to C, but that doesn't mean that you can come back if it is a directed graph. Okay. So another thing that I miss if I don't use graph is that A and B are connected or A and P are connected, right? But I don't know how they are connected. If I use a union find, I really don't know.
Yeah, right. You just know
So
that.
so you say we should try union find whenever we see a problem as a graph and it's not directed. Correct?
No. Just
no, I mean not go for it, but like analyze. If it's directed, then there's definitely you can't apply union find. But if it's undirected, then there's a possibility.
So here is the thing, right?
If the transitivity.
Yeah, if they're transitive. Okay.
Yeah. Suppose you are given a graph problem and you said that find a path from A to B. It is undirected graph. And you are given saying that is there a path exit between A to B? Or find a path, shortest distance. You can't use union find there because those are the properties that you lose when you use union find. You lose that what is the path, how they both are connected.
The reason that we lose the path is because we do the path compression.
Yeah.
If we don't do the path compression, then we still have it.
But that would defeat the purpose of using a disjoint.
Yeah, but at least we can find out if there is a path. If the problem statement is just find the path,
if there
is a path, you can use union find. It's very quick, right?
Yes, so I agree. So yeah, that is where I want to come, saying that not all graph problem can be solved by union find, but the portion of it where you don't really need to answer saying that whether there is what is the path, but you have to answer saying that whether they are connected or not, whether there is a path or not. You can easily solve using union find.
And sometimes you want to actually preserve the path, so you don't want to use union find. Like for example, yesterday in the word ladder problem, you want to find the length of the path. So using union find won't help you there because it'll just give you a path of 1, for example.
Yeah, perfect example. Yes.
What if we keep the extra array outside union find and say that the parent would it be sufficient to find a path?
No, I think no, because you do path compression now, so you lose all the ordering.
No, what he's saying that if we maintain another array with saying that from where to where came, but I think it will be, I'm not sure. Okay. Basically, if you see the graph problem, we do exactly same, right? We just keep the parent one array. That's it, that which is my parent. And then when we have to reconstruct the path, basically we go through that. I'm not sure. Okay. Maybe intuitive idea, it is possible, but if we are doing that, then probably you don't need union find. If you really need path, then union find is overhead. I think graph problem will give union find is extra. You really don't need it if you really need path.
Compress in that case, right? If you don't compress, then you'll continue having.
Yeah. But that's I think then it's a similar. I think the other graph algorithm work that way only, right?
Yep.
The finding the path between two nodes in graph works that way only. Okay. I had a fourth problem also, but I don't think so. We have time. Maybe we can discuss. This is also a very interesting problem, but it is very simple to solve. Number of island.
Yeah, I did it a couple of days back only.
Yeah. So again, similar code. We can
the code.
Sorry.
Probably, if you can share the code, we can go ourselves.
Sure, I'm gonna share code for all these 4 problem. Okay, quickly, it is again same using the union find. So I would want to stick with same union find code, and then try to. This is the only extra code on top portion that we have written using the same union find and solve it. Okay, I'll share that code.
Where usually you share the code?
Normally we share either in the chat or we share into we have a GitHub, right? What is anybody remember?
It was SDE.
Here, I think.
Yes.
I can basically put all 4 code here. We have SD
handouts,
skills, meetup, hands out, and code.
Yeah.
Okay, on GitHub.
And you give the link of this GitHub?
Yeah.
Sure.
So one thing I want to ask, so basically that bot posted on LateCode that there were 3 different problems, right?
Yes.
So how do we do we solve those problems or we take different problems?
Okay, so let me stop this recording. Okay, this is not related to this topic, but I can still talk about it. Okay, let me just stop recording.